Welcome to The Explainer. I'm really thrilled you're joining us today because we're going to tackle something that impacts literally every single one of us every day, and you probably don't even realize it's happening. Have you ever stopped and wondered how systems engineers actually calculate what is considered safe enough? Well, whenever you step onto a train or just walk through an automated gate, a massive amount of mathematical and philosophical heavy lifting has already been done behind the scenes, just to make sure you get home. So today, we're going to demystify the mathematics of danger. I want to kick things off by asking you a rather provocative question. Is absolute safety an illusion? It might sound totally crazy to hear this out loud, but governments and safety engineers do not design systems to be completely 100% safe. They just don't. They design them acknowledging that some level of risk is actually acceptable. I mean, we routinely accept the risks of flying or even just crossing a busy road because of the benefits we get out of it, right? So the ultimate challenge for engineers isn't to somehow magically eliminate all danger, but to systematically calculate and control it. Here is our agenda for today's explainer. Number 1, defining acceptable risk. Number 2, qualitative risk assessment. Number 3, the risk matrix. Number 4, quantitative risk assessment. And finally, number 5, the ALRP principle. Okay, let's jump straight into section 1, defining acceptable risk, specifically looking at hazards versus risks. To really understand how we measure danger, we first have to separate two words that people use interchangeably all the time, but they are very different. A hazard is simply a condition that could lead to an accident. You can think of it as a potential source of harm, or quite literally an accident just waiting to happen. On its own, a hazard hasn't actually hurt anyone yet. It's just sitting there in a dormant state, waiting for a very specific trigger event to set a dangerous sequence into motion. For example, an unprotected, active railway crossing represents a classic hazard. The crossing itself, with these massive trains speeding by, is absolutely a dangerous condition. Now, there isn't an accident happening in this exact moment, but the hazard is very, very real. All it takes is a trigger event, like a car approaching or a pedestrian who forgets to look both ways, to turn this waiting hazard into an actual catastrophe. And that perfectly illustrates how we transition from a mere hazard to calculating actual risk. You see, risk isn't just the existence of danger. It's a mathematical combination of two specific variables. It's the likelihood of the accident happening multiplied by the severity of the harm if it actually does happen. So if we want to keep people safe, we have to either reduce the likelihood of the event, reduce the severity of the damage, or ideally do both. Section 2, Qualitative Risk Assessment. This is the framework of expert judgment. Now that we know what risk actually is, how do we first measure it without relying on mind-numbing amounts of raw data? Well, in qualitative assessment, a panel of experts uses their deep systemic knowledge to categorize the likelihood of a dangerous event. They rank it on a structured scale, so at a level 5, an event is classified as frequent. Then, moving down the scale, the probability drops through probable, occasional, and remote, all the way down to a level 1, where the event is considered completely improbable. Next, these exact same experts independently categorize the second half of our risk equation, the severity. Basically, if the event does happen, how bad is it going to be? This scale ranges from a level 1 negligible event, which is just a non-reportable trivial injury, and scales all the way up to a level 5 catastrophic outcome, which tragically translates to multiple fatalities. Moving right along to section 3, the risk matrix. This is where we intersect likelihood and severity. But how do we measure what we can't always intuitively see? We literally smash those two independent measurements together to create a risk matrix. By plotting likelihood on one axis and severity on the other, the resulting risk falls into very strict operational zones. Think about it. If an event is frequent and catastrophic, it enters the intolerable zone. That activity is simply shut down, not permitted. On the flip side, the low-risk zone is broadly acceptable. But that middle area, the medium and high-risk zones, that's where things get really complicated. This is the tolerable region where control measures absolutely, legally, must be implemented. Which leads us to section 4, Quantitative Risk Assessment, the numerical prediction. While those qualitative categories are fantastic for establishing a baseline, what happens when we're dealing with a highly complex system, like, say, a fully automated train network that requires absolute pinpoint mathematical precision? We have to contrast the approaches. On one side, we have qualitative assessment, relying on expert judgment. On the other side, we have quantitative risk assessment, or QRA. This relies purely on the hard numerical prediction of the probability of harm. It totally removes the subjectivity of human judgment and replaces it with cold, hard statistical facts. To pull this off, engineers use QRA tools to assign incredibly precise failure rates to individual system components. They use these highly logical deductive frameworks. Take fault tree analysis, for example. It tracks every single sequence of events that could possibly lead to a failure, mapping it out like this massive tree of cascading errors. Or failure modes and effects analysis that looks at a single component, figures out exactly how it might fail, and calculates the exact probability of that tiny failure impacting the whole system. By doing this for thousands of parts, engineers can calculate an exact numeric final outcome probability for a catastrophic failure. It's honestly mind-blowing.
And finally, Section 5, the ALARP Principle, the economics of safety.
This deep numerical understanding of failure brings us to our final concept, and it perfectly bridges the gap between engineering, law, and economics. This is the ALRP principle. ALRP stands for as low as reasonably practicable. In many jurisdictions around the world, like the UK, this isn't just a polite suggestion. It's a foundational principle dictating that projects are obliged by law to relentlessly reduce risk to this specific level. But pay close attention to the phrasing here. It doesn't say as low as absolutely possible. It says practicable. So you have an unacceptable region of risk at the extreme top and the broadly acceptable negligible risk at the bottom. That massive area in the middle is the ALRIP or tolerability region. Engineers are legally required to drive the risk down through this region. However, and this is a big however, risk reduction is continuously implemented until it hits a very specific economic wall. Here is the crucial takeaway. A measure is not reasonably practicable if its cost is grossly disproportionate to the benefit it provides. This is exactly where safety engineering morphs into economics. Picture a giant balance scale. On one side, you have a massive bag of money, and on the other, a tiny shield of safety. If an engineering upgrade costs $1 billion, but mathematically only prevents one minor scraped knee every 100 years, the cost is grossly disproportionate. The law actually allows engineers to stop mitigating risk at that exact point. Let's see how this plays out in the physical world using the hierarchy of control. When engineers encounter a hazard, they have a menu of options. The absolute most effective option is at the top, elimination. For example, replacing a dangerous level crossing with a multi-million-dollar bridge. But remember ALRP? If that bridge cost $50 million for a quiet dirt road in the middle of nowhere, it might be grossly disproportionate. So they move down the hierarchy to cheaper, albeit slightly less effective options. Engineering controls like automated lights, administrative controls like warning signs, or relying on personal protective equipment. Engineers constantly balance this hierarchy against the strict mathematical limits of ALRP. Understanding this completely reframes how you look at the infrastructure around you, doesn't it? The world isn't designed to be completely safe. It's designed to be optimally safe based on calculated math and acceptable economic thresholds. So next time you cross a street, pass an automated gate, or ride a high-speed train, just look around at the warning signs and the structures. Ask yourself, at what point did an engineer calculate that your safety was finally worth the cost? Thank you so much for watching, and keep asking the big questions.